6.3 Volumes, the Disk and Washer Methods. In an earlier chapter, we used integration to evaluate areas of regions. Now we will explore ways that integration can be used to find volumes of solids formed by rotating a region about some given straight line. If a region in a plane is revolved about a line, the resulting solid is a solid of revolution, and the line is called the axis of revolution. The simplest such solid is a right circular cylinder, or disk, which is formed by revolving a rectangle about an axis adjacent to one side of a rectangle. So if we had a rectangle, let's say that this was going through the line y equals 3, and let's say this was going through the line x equals 4, and we revolved it about the x-axis. We would just be spinning it about that axis, and what it would end up happening is that you would get this cylinder that looks like this, where the radius of the cylinder is actually this distance, right? And so that ends up being the radius of your cylinder. And so, this would be, the height of your cylinder would be, from, you've got your 0 to 4 there, so that'd be 4. So that is what we're going to do. That is a way, that's a way to produce a cylinder, is by taking a rectangle and spinning it. Now you could take that same rectangle and spin it about the y-axis, and then that would produce this cylinder. And this would be your radius. Okay? So that's what they're talking about there. So now, what if we took a linear function, and so you can see that what you have here with the x-axis and the y-axis is your is a triangular region. And what if we spun that, and for just for right now, what if we spun it about the y-axis? So you're imagining that this is just spinning, and it creates this cone here, and the cone ends up with a height of 2 and a base radius of 6. But what we're going to do in calculus is we're going to use calculus to figure out how to find the volume of this by slicing it into regions. So what we're going to do is, since we're spinning this about the y-axis, we're going to draw something called a representative rectangle perpendicular to your axis of rotation. So you want your representative rectangle perpendicular to the axis of rotation. And you're going to be doing this every single time, so you need to remember this. And then when we've got this, as you spin it, it creates, these circular regions, of course, so that if I cut this at any point, it would produce this disc right here. So just by slicing it, you're just finding that representative rectangle is for a little slice of your three-dimensional figure. You're imagining that, hey, if I took this representative rectangle here and I sliced it, this would be the radius of my little disc. And what I like to tell you to do is find a point on your function at the end of that representative rectangle. That's an xy point on your function. For this one, they gave us this function, x plus 3y equals 6. And with this distance right here for this point, imagine that you're going to that point, you go x, and then you go y, right, to get to this point. So you can see that this distance along your representative rectangle is the x of it. You also can see that the width of it is a delta y. Like that's a change in y. That's the width of your, see how that's dy? So that's delta y. It's going to turn into dy when we make it an integral. But so since this is the y of your xy point, you want to solve for x. Okay? You're solving, sorry, I said it was the y. This is the x of your xy point. So you're solving for x. But it's going to be in terms of y. Sorry about that. So now, if you're going to write your volume, you've got your volume equals. We're going to do y integration for this one. So your y integration, look, goes from 0 to 2. 0 to 2. And we're going to say this disk, the volume of it, is the area of the base times the height. So this is pi r squared times the height. So this is pi x, because they just called that x, pi x squared times the height, which was your delta y. Well, your x for this particular problem is your 6 minus 3y times delta y. So that's the volume of this disk. You're going to add up infinitely many of them. So that's why we're doing integration, right? The integration means from 0 to 2, we're going to add up infinitely many of these. And what ends up happening is we end up getting the volume of that whole cone. So now bring that pi in front, integration from 0 to 2, and we're going to multiply. So now this is going to be 36y minus 18y squared plus 3y cubed from 0 to 2. And we put our 2 in. And then if we put our 0 in, it just gives us 0. So we're not going to worry about that. This is going to be 72 minus 72 plus 24. So our 72's cancel. We end up with 24 pi units cubed. Okay, so that's going to be the volume. Now, since we know that this is a nice cone, we can check our work using our geometry formula. Volume equals 1/3 pi r squared times the height. And for this one, our radius of the base was 6, and our height of our cone was 2. So 1/3 pi 6 squared times 2. So 36 times 2 is 72 pi over 3. 72 divided by 3 is 24. So it does check out using our formula. The thing is that not a lot of these actually have a formula. You know, we're doing the easy ones first. We're able to check the ones that do end up being cones and, you know, triangular prisms and things like that. But most of them do not have a geometric formula. So now, that moves us to, when finding volumes of a solid of revolution, it is important to focus on what happens to each individual strip or disk as it is rotated around a line instead of thinking about the total volume. A thin slice or strip can be horizontal or vertical, and the volume of the disk sliced vertically. So of course, if I was slicing it, and notice that this is still a cylinder, so you're still, you know, talking about area, you know, pi r squared times the height to find the volume of that. And it just depends on whether you're going to do it with respect to x or with respect to y. So for horizontal axis of revolution, we're going to solve in terms of x. So if we're revolving around the x-axis, that's horizontal, or any y equals plus or minus k, because sometimes they might say, spin it about the line y equals 2, or spin it about the line, y equals -1. A vertical axis of revolution, it'd be the y-axis or any x equals plus or minus k. So they might say revolve it around x equals 2 or revolve it around x equals 1. So we're going to practice those as a separate lesson, but just so that you know, this definition is going to work for any of them. All right, so now let's look at example number 2. The first thing we're going to do is sketch a graph of this. So I'm going to know that this goes through the y-axis at +1, and it has a -1, +1 slope. So I just did rise over run. I went -1, and then I went +1. And this is my linear function. And I'm going to go ahead and shade the region that they're talking about. Okay, they're talking about that region that they didn't really say, but had they said, like they might have said the line x equals 0, y equals 0, and y equals -x plus 1. They might have said the region that was bounded by those lines. And then they did tell us that they wanted us to revolve it around the x-axis here. So we imagine that if we revolved that around, that it would produce a sideways cone like that, okay? So we will be able to check this one with our formula, but we're going to use calculus. So here's our representative rectangle, and it's perpendicular to our axis of rotation. I want you to notice that the thickness of that is along the x-axis, and so that is a delta x. So I know that my integration is going to be in terms of x. Now I'm going to pick a point at the end of that on my function, at the end of that representative rectangle, and that's an xy point. And again, here's your x, here's your y. It is the y of it. So the y would be in terms of x. So this radius, because remember, we're slicing it, that representative rectangle, it is the radius of a slice like that radius, right? So we're imagining that we just took a slice out of here and that it looks like that. And that thing right there is the radius of it. So we want to find the volume of this. And so this would be pi r squared times the height, with that being the height. So this is pi, and now we said that this is going to be the y of it, so that's -x plus 1 squared, and then your height is going to be your delta x. So to find our volume, integral, and we're going along the x-axis from 0 to 1. Pi r squared times the height. Our delta x turned into dx. And we're going to square this. And now we're going to integrate. And we're putting a 1 in. And then when we put a 0 in it, that one turns to 0. The positive 1 and the negative 1 go away. We end up with pi over 3 units cubed. And so now we can check it using volume equals 1/3 pi r squared times the height. Now remember, that is the bottom, you know, it's the area of the base. So the base has a radius of 1, because this would be the radius of your base. So your radius is 1. Your height, this actually would be your height, also is 1. So your radius is 1 and your height is 1. So this is 1/3 pi 1 squared times 1. So you can see that it does check out using our formula for the volume of a cone. But we used calculus. All right. I'm going to stop and just make sure this video is working, and I'm going to have to split this into 2 videos.